There we go. Looks like we can get going. Well, welcome back, everyone. We had our first exam and now it's finally been passed back. Usually I try to get them back sooner, but sometimes I'll be in the middle of the week on a Wednesday is probably the more likely time. For our first exam, the average came out to 80.5%, which is really excellent for this kind of class, I'd say. It's definitely tough, especially on exam one, when it was all those vocabulary questions we had to get through. I think that was the hardest part about the exam. But there was a maximum grade of 100% as a three-way tie. So congratulations to those students who obtained that grade. It takes hard work to get 100% on this kind of exam, I'd say. It probably took lots of reading and lots of practice and study to get there. When you open up your exam, I gave two scores, which is kind of confusing in all honesty. The first score you got was just the maximum points you obtained out of the possible 48 points. So you have a fraction right here. When you go to check out your grade in Moodle, that fraction is converted into percentage just because that's how Moodle decides to work with those things. And also you have a course score right here. The purpose of the course score is just your standing in the class as of today. I updated the web assign, I believe, on Tuesday, so it's not fully updated, but it took into account your web assign grade, your quiz grades, as well as your exam one grade. So keep in mind, those are the two different scores. And if we take a look at the syllabus, I just want to show you how I calculate your course grade. What I did was just take what your web assign is on the date that I put in the grades. I believe, again, that was Tuesday. And that's only on the assignments that were past due. Then 10%, I took the average of your quizzes. I believe that was quiz 1 through 4. And the last thing I did was exam one is being weighted as 70% for the moment because it's the only exam that we have out. So that means when I give you your course grade on exam one, there is a lot of flexibility right here because an exam one is only going to really be worth, let's take a look, 40 divided by 3 percentage points. So not the full on 70% right now. Also, if you feel like you are not completely happy with your grade, you want to bring it up, there's definitely a couple things you can do. Go into WebAssign and you can always request an extension. And if it's giving you trouble in there, there's been a couple people who have been having trouble with extensions. Just send me an email. I'll go to your WebAssign account and extend any section that had gone past due without completed. So you could just email me if that's more convenient. I'd be happy with that as well. Also, at the very end of the semester, we'll have the extra credit opportunity we mentioned before as for exams. So your final exam score will replace your minimum among exams 1, 2, and 3. So those are things you can do to bring up your grade. And let's go back to about here. And after each exam, I'm always going to post the solutions like this. The major reason is, well, it's just interesting to see the solutions. I always appreciated it as a student. They'll be really helpful once we are way down on December 11th, studying for the final exam. We'll take all of our exams and I'll give you a sample final exam, several versions. One of the versions is just going to be a blank exam 1, exam 2, exam 3 thrown together. So to see just how good are we at those questions if we run through them again. So you have the solutions always available after each exam. Well, that's my full spiel. And I'll turn it over to the class. Well, before I do that, let me pass back an exam first. So now, like I was saying, I wanted to turn it over to the class. After we take an exam, I'm very happy to take any questions you might have on it, on either problems or just general questions. So any questions at all, folks, that you would like to discuss? Okay, well, if there's no burning questions, we can get going on the notes. But if something does come up and you want to circle back to that, don't hesitate to throw it out there. I'll be very happy to come back. So here's where we're at so far. Once I get the Moodle to settle, here we go. Right about there. We're just about done with section 3.5. And pretty much it's really just based off of this curve right here. At the moment, this is called the empirical rule, but we're going to start to call it things along the lines of normal distribution or normal model once we start doing more and more probability. So also, if we go down below, we have our 5th quiz that's posted a little bit early, and we'll talk about that again on Thursday. So if we open it up again, or right now, just in case we forget on Thursday, let's take a look at it. Pretty much what's going on in quiz 5 is we're dealing with the normal distribution. We're going to draw that normal curve, the 68 to 95, 99.7 rule. So we'll have a picture here and same kind of questions like you saw in the notes. So let's get started then. We're over here in section 3.5. Here, again, this is sometimes referred to as the empirical rule. Or it might be called the 68, 95, 99.7 rule. That's dealing with the percentages. As you go from 1 to 2 to 3 standard deviations out, you accumulate these percentages of data. It could also be called the normal model or curve, or it could be called, it has too many names, honestly, the normal distribution. So that's the object that we were working on last class. And now we're going to give it another try in example 4. Any questions first, folks, with dealing with this model here? Okay, the main takeaway is when you see a curve like this, it's not as much about the curve as it is about the underlying data. So if we scroll up for just a moment, scroll way up, here we go. This is the ideal situation where you grabbed a random sample, say maybe 100 observations, you put all the data into a histogram, and it turned out highly symmetric, unimodal and mound shaped like this. Then the normal curve or the empirical rule that we've been discussing is essentially that curve. It's trying to tell us where all the data is concentrated, where it becomes really sparse on the tails and so on. And with using that model, we can now ask and answer questions about the underlying population, even when we didn't take a census. So just with sample data, we can start doing modeling, discussing the underlying population. So here's where we left off before. On example 4, it says, the time it takes a driver to react to a brake light on a deaccelerating vehicle is critical to avoiding rear collisions. That's really just context to get us into the frame of the problem. And what they did in the actual study that was published here in Ergonomics 1993 was they had reaction times for an in-traffic response to a brake signal from strand brake lights. So a lot of people were tested, and they found that people reacted on average 1.25 seconds to the brake light with a standard deviation of 0.46 seconds. So with that out of the way, what we're going to do is draw the normal model to match up that data and start answering these questions down below. This will come into play at some point, so let me move it down so we don't have to scroll a bunch. I'll put it right here just temporarily. Any questions at all first, folks, before we get started? Okay, well, first thing we want to do for drawing a normal model is, or a normal distribution or anything like that, is just draw a long horizontal line. So here it is. Then attempt to draw that bell-shaped curve that we saw before. Only thing that we can't do is anything that goes like this could lose credit because it can never even touch the x-axis, let alone cross it. And we shouldn't have anything like this, for example, because the tails on the left side and the right side have to get close to the x-axis, again, without touching it or crossing it. Another thing we can't draw is anything that goes like this, because there's no points on a normal curve. It's a nice, smooth curve you could never cut yourself on. So if your curve looked about like this, then I wouldn't be too picky about that. It's not great, honestly. I kind of flubbed it right there. It is touching the axis, but not crossing. But I would give full credit to something like this. So try your best to make it look readable because we have to use it for the follow-up questions. But aside from those two comments, I won't be picky on grading these kinds of things because I'm not a very good artist myself. I've practiced this for a long time with very, very little results. And that's not a very good one, in honesty, but that will stand. That's probably my best one today. So let's let that be our model. First thing we do is we put a number directly right here. It's going to be where the data is accumulating, the center of the distribution. That's what the sample mean X bar is referring to. So we'll put here a 1.25. I'm not picky on units, but we mentioned before, units really help a lot. I wouldn't put units on every one of these tick marks. I would put it out here. This is seconds. And sometimes it's a good idea to be even a little bit more specific. This will help you solve the follow-up questions. This is seconds to respond to brake light. So that's what the data represents. A really good idea to put it on this axis because it'll help us anytime you see this kind of question. Give a practical interpretation. We have to have a really good feel for what is the context to begin with. Once we have that, we're just taking the 1.25, adding the 0.46 seconds. That'll give us a value here. Do it again for the second value and again for the third value. So now it's time for our calculator. So first 1.25. Add to it to the 0.46. That's going to be our first value, 1.71. Then just keep on going. There's actually a good shortcut to this. If you up arrow or hit second and enter, either way you'd like, I'll use the up arrow trick. Up arrow until this is highlighted, hit enter and go ×2. That way you don't have to retype this every single time. It's just a quality of life type of improvement. So here's adding 2 standard deviations, 2.17 seconds. We'll do it again, hit up arrow twice, enter, and then left arrow, so it's ×3. Again, that's just to save us a lot of time in plugging all these things in. So last one is 2.63 seconds. Going to make that black line just go a little bit further. There we go. Once we get the right-hand side, we just redo it, but using subtraction. Does that look right to folks so far on the 3 numbers to the right? Okay, well, that was so fun. We'll do it again, but now we're subtracting. First, I'll put down the tick marks. 1, I'll keep it in green so they look the same. So 1, 2, 3 going off to the left. I'll use the same trick up here. Let's up arrow twice. Hit enter. I'm going to just delete right here. Go all the way in the middle and put in the minus sign. Again, you don't have to use these kind of calculator tricks, but if you have to type this in multiple times, like say 6 times altogether, at least for me, I have a really high chance of making at least one mistake, unfortunately, because of just all the key jamming. So if you can make a shortcut in the calculator, it's really for accuracy more than anything, which is big on WebAssign. So here's our first value, 0.79 seconds. And now something weird is going to happen to the scale. But let's keep on going. I'll hit up arrow. And this time go ×2. We're subtracting 0.46 twice that way. Now we're at 0.33 seconds. I don't like that decimal point. Let me try to make it look better. And one last time. Up arrow 2 times, enter, go left and just change this to ×3. And that's the one thing that just doesn't look too good, does it? It's negative 0.13 seconds. And it's actually not that we made a mistake. The mean is 1.25, the standard deviation is 0.46. If you subtract 0.46 3 times, you just end up at a negative value. So this problem is already weird, right? You can't react in a negative amount of time to a brake light. It sounds like time travel or something weird like that's broken. But that's what we're going to address on part C, or excuse me, on part D. Before we trust the results of what we're about to produce, we wonder what further facts we need to know about the original sample data. Just because we have sample data like these, doesn't mean the model is a good one necessarily. Now, this isn't too bad with a negative here, because right where the red dot is, that's 0.15% of all of the area under the curve. Well, if that's the case, That's a tiny, tiny amount, but it's still indication that there's something flawed about our problem. So the hint to this, we'll turn back to it when we get to the last portion. Sorry, go ahead.
Maybe it could be negative reaction time from the light changing when like you could see a civilian like pressing on the traffic lights.
Oh, I see what you're saying. Yeah, it could be something like that.
Could be more intense rather than a reaction time to seeing the light.
I like that. That's a great way to think about this one. I think it probably wasn't that, only because this was published as this article in that particular journal. There's a good chance it was like a controlled environment and everyone was like in a test room where it was just like a fake brake light and a fake pedal for the brake that you would hit on. So only because it was this kind of study, it might have been more controlled. But if we didn't have that information, that's an absolute plausible reason for negative values right here. Now, one thing that could be happening is we look at the normal model, the empirical rule, once again, there are conditions on that thing. Your data has to be mound shaped. It has to be approximately symmetric. And the more we violate those conditions, the weirder it's going to look when you actually try to use the model. So in other words, if you saw negative values that didn't even make sense, situation might be this. Our data was actually skewed. We don't even get to see the data on this problem, but that might have been what was happening to the underlying data. Well, in either case, that's definitely weird. So we'll try to just think about it as we get through the problems and see what's coming next. Any questions so far? Okay, so these instructions are really kind of interesting. Part A is one problem. It really has a lot of subparts. We drew the normal distribution. There it is, the black curve. We've labeled it. That's the horizontal axis. But we haven't done this, show what the empirical rule predicts. That's the percentages of the area under the curve or the percentages of the observations that it's predicting. So last thing we do is either see this right here, by the way, really great to have for your exam 2 notes, something like this, and just start putting in all of those percentages. So I want to just take a different color here. Let's go with plum, I guess that'll work. So right where we put in those tick marks in green, that's the standard deviations we are away from the mean. You could put 68% in the middle or do as our author does and break it up like this. 34% goes here and 34% goes into that location. Then if we go one to the left, it's 13.5%. But there is full symmetry here, so it must be exactly 13.5% on the section over here. Then down the line, 2 more percentages. In this location, it's a 2.35%. So go across the mean in blue and put the same value out over here. And last one, this one is not in the book. We put it on the notes in Moodle, so good idea possibly for the exam as well. This is 0.15%. Here and here. So finally, that does the job, folks. That's the normal model, labeled on the horizontal axis, and we also know what the rule predicts with all those percentages. Any questions at all on that full construction? Okay, the good news about this is, even though it's a lot of writing and drawing, every problem goes like this. The only thing that will change is the mean in blue and the standard deviation in green, which updates all 7 of these numbers here. The rest of it is a guarantee. So that helps out tremendously, I'd say, for producing these things. Now we're getting into the different kind of questions, percentiles type questions. So it asks us in part B, what is the approximate value of the 2.5th percentile? Then we'll give a practical interpretation. So we'll focus on getting the number and then return to that word right there. So let's take a look at the definition below. If we say rth percentile, say 2.5th percentile in our current problem, it's a value on the horizontal axis itself such that our percent of observations in the data fall at or below that value. So if we're asking for the 2.5th percentile, we can't be, say, over here by 2.17 because we're looking at around 80% of the data to the left. The 2.5th percentile ought to be somewhere around here. It can't be 0.13 because that's 0.15% of the data to the left. Well, if we go right here, 0.33, let's take a look. At 0.33, we have percentages 2.35 plus 0.15, which matches up exactly to 2.5. So because we have 2.5% to the left of that value 0.33, that is the 2.5th percentile. It's kind of tricky, so let's see if we can draw this out. So I'll just take a quick screenshot here. And for the sake of the notes, our explanation will be right here. So the thing I would highlight probably for this kind of question is when it says 2.5th percentile, it's going to be this number because these add up to 2.5%. So going back up to the top, we can say 0.33 seconds is the 2.5th percentile. Any questions at all, folks, on finding that value here, the 0.33 seconds? Okay, if they said something like, say, 84th percentile, then we want to find 84% of the area under the curve to the left of that value. But here at 2.5, it's the 0.33, only because of those two numbers right here adding up. So we've got it, folks. That's the value we wanted, the 0.33 seconds. But here's where it gets a little bit tricky. I'm going to be using this word right here a lot in this class. So you'll see this on quizzes, exams, lots on lecture notes. You'll see it in WebAssign as well. But on WebAssign, because it's a computer program, these usually come out as multiple choice. There, we're really just practicing these kind of questions. A practical interpretation always uses the context of the problem. So anything you put right here to remind you of the context, it's going to help you out a tremendous amount on this part B right here. So here's what a practical interpretation will go on for this one, or look like. We'll say approximately 2.5% of the observations in the study had a brake light reaction time of 0.33 seconds or less. So that's finally our full interpretation of this. Does that make sense to folks so far? Awesome. So if we said it a slightly different way, take everyone that was a participant of the study, about 2.5% of them were just really, really fast at reacting. Maybe they were pro gamers or something along those lines, and they're just really good at reacting to lights. And they reacted at 0.33 seconds. But don't forget this statement, or less. That includes everyone that was even faster than 0.33 seconds, but also goes to the negative region where those values are actually impossible. So that's why we say approximately. Even when the model works well, all of this is approximate values. And when the model performs not so well, like with the negative numbers, it's a strong approximation. We don't expect full accuracy here. We're just going based off the information we were given. So that's our first one down. Any questions, folks, on getting that 2.5th percentile? Okay, so if we look at small percentiles, we're always on the lower end. Let's say like on question part C, that's asking for 84th percentile. We're somewhere on the upper end, like the 2.17 or maybe the 2.63 seconds. So let's do a redo on this and see how it goes for a higher percentile. So it says, what is the approximate value of, now it's 84th percentile. By our definition, which I should not have deleted, let me bring that back. By definition, the 84th percentile is going to be some number on this horizontal axis so that 84% of observations are to the left of that number. So if we had a guess, any volunteers for a guess on which number it might be?
Wouldn't it be from, let's say 55 to 1, no, sorry, well, I read the wrong thing. Okay.
Oh, no worries.
The point of negative 1.13 to 2.17.
So about right there is where you're indicating. I believe you're right on that one. Let's take a look. So if it says 84th percentile, that would mean 16% of the data is to the right of that value. So I think at 2.17, it might be just a little bit further to the left at 1.71. But let's take a look at this and see what happens on this location. At 1.71, the area that goes to the left would be all of this stuff. And it needs to fall into 84% exactly when we tally those up. Or another trick, to the right, that should be 16%. Does that make sense to folks so far? Awesome. I'll do it going to the left because, I mean, that's what the percentile means. We don't need to do it a fancy way when we're just looking at the definition the first time. At 1.71, if we add up all these percentages to the left, here's what it would look like. Starting at 0.15, add 2.35, then add, I'm up to here, the 13.5. Then we're getting through it, 34% twice, so just 68% altogether is a quick way to put it in. Adding this all together does get us right onto 84%. So that means the value 1.71 itself is the 84th percentile of these data. Does that make sense at the moment? I'm finding that 84th percentile. Awesome. So it just means 84%, like our calculator says, of the data is to the left, which also means 16% of the data should be to the right. That's a little bit easier to check. So our answer on this one will be the 84th percentile is 1.71 seconds. Now all we have to do is give the practical interpretation of what that means exactly as far as the context goes of the study. So let me grab this right here just to indicate where we solved that second portion. And any volunteers at the moment for putting out a sorry, go ahead.
Approximately 84% of the observations, but it won't really or that.
Awesome, that's exactly what it would mean. 84% of the participants in the study had a break light reaction time of exactly as you said, 1.71 seconds or less. Always good to emphasize that because it's really talking about a whole range of values going off to the left. I'll put this in a color to highlight it, or maybe better, let's just put an actual note. The note I want to put in is, don't forget this part. Saying the or less is what makes it a percentile because it's all the values to the left of that particular observation, 1.71 seconds. Well, we did it, folks. That's percentiles twice. Any questions at all in these interpretations or getting the values? Okay, again, it's kind of a scary study when you look at it because if 84% of the observations took 1.71 seconds or less, well, 1.71 seconds isn't great for a brake light response. Say you're going down Anderson on a rainy day doing 35 miles per hour. 1.71 seconds is a lot of distance that you're covering. But it's also saying if 84% take 1.71 seconds or less, 16% of those same participants in the study took 1.71 seconds or more, going off to the 2.63 second range. Some of them may have potentially been around 3 seconds, although that would have been quite far away. That's in the 4 standard deviations territory. But we expect around 2.35% to be between 2.17 and 2.63 seconds. So that's kind of a scary thought as well for these data. But all is not lost because we also know this is just a model. It's trying to predict a reality, but it can only do so well. We always expect there to be an error in this kind of work. If you saw negative values right here, the error could be substantial. And that's what part D is getting into. It says, before you trust the results in parts B and C, here's our part C right here in our interpretation. What further facts would you like to know about the sample data from the study? We want to mention 2 facts. So I'll organize it this way, fact 1, fact 2. A volunteer for what the first thing we require if we use the normal curve. One thing you can think about is, what about skew? Could we have used a normal curve, the 68, 95, 99.7 rule for skew data? I agree, some folks are shaking no, and yeah, our data has to be at least approximately symmetric. That was the very first condition. So let's take a look up here, back where that rule first showed up. It needs to be mound-shaped and approximately symmetric. So that could be our two really fast conditions that we need. Let's say right here, the 2 facts we need in order for us to trust everything we put up here, the practical interpretation and all, is that first, the data must be at least roughly symmetric. So if it looks like it has a slight skew, one direction or the other, that's not a big problem until the skew becomes severe. Once that happens, then the whole curve right here that we try to draw completely falls on its face. And it gets even weirder. Symmetry is not enough. Your data could be absolutely perfectly symmetric, and still this empirical rule just is not going to work for us. Say, for example, our data look like this. Let me put it down here since it's a side comment. If we took our data, put it into a histogram, and this is what we had, these are pretty weird looking and kind of rare data to get out, depending on what you're doing. But you can get data that looks like this. What I'm trying to do is make all of the heights of the rectangles in the histogram to be about the same height. They kind of jitter up or down based off location, but that could be just due to randomness in the sampling. Anyone recall what kind of histogram this would be if we described its shape?
Uniform.
Good call. This is uniform data, and uniform data is kind of scary. Let's put it here. It's symmetric, uniform, but here's its problem, but not mound shape. Why is that a problem? Well, when the author says mound shaped, she's referring to this shape here. Sometimes people just say bell curve. Mound shaped is probably a good call. It sounds more descriptive. Try to put a mound shaped bell curve to the uniform data, and here's what it looks like. It does an absolutely terrible job. You want your curve to be hitting the heights of each one of these rectangles, so it fails off to the left, fails off to the right, and it even fails in the middle because there's a bunch of missing area right in this location. So if we have symmetric data, the punchline is that's still not good enough, unfortunately. And that's what condition 2 is really referring to when they're saying, what do we need in order to trust our results? Let me first put a quick order here. Now let's just say briefly, the data must be, you could say mound shaped or uniform, or excuse me, not uniform, mound shaped or bell curve. Let's go with mound shaped. Insisting on that throws away symmetric uniform data like these, which are a problem to analyze since the normal curve just doesn't work for them. Well, any questions, folks, on getting through this question here? Yeah, go ahead.
A negative number, I think there at the negative question, so that always be an indicator to you that this is not going to be fitting into the empirical thing.
I would say yes, unless you're talking, if the negative came out to like 4 standard deviations or 5. But if you saw negative numbers and they didn't make sense in the problem, and you're within 3 standard deviations, I would say that is a decent indicator. But what I would also say is, at that point, you should request, where's the data, where's the histogram, so we can take a better look. Because it could have just been like this. This is really a boundary case because it was 3 standard deviations. If it was way out here, maybe closer, or maybe in the 2 standard deviations location, at that point, I would say, yes, our data is weird. It's either skewed or maybe something more esoteric like the uniform distribution in that case. Yeah, negative numbers are a worry. We're just lucky it was on the far left 3 standard deviations. Other questions so far? Okay, well, we did it, folks. That's dealing with this kind of information here, working with the normal curve, as we so called it. One thing that's kind of tricky is every question you do on this has to line up exactly to one of these standard deviations. So when you go to do this as a quiz problem, say quiz number 5, the sample mean is 532.2, the standard deviation is 166.4. But any of these questions here, like the 33 and the 698.6, they have to line up exactly on the normal curve that you're about to draw here. In other words, my questions have to be relative to these 7 different numbers along the horizontal axis. So if it doesn't line up when you drew it, there might be some mistake in the calculator, maybe a rounding error or something like that. So there's kind of a built-in check inside these kind of problems. But for the moment, let's now save this and turn to the next chapter. Excuse me, not the next chapter. I forget. Thank you. We're going to 2.4 next, before we go to chapter 4. So what's happening in 2.4 is we're going to be treating bivariate numerical data. So in other words, think of 2 numerical variables. They can be continuous or discrete. And we just want to see how to plot with them and how to analyze with them. Our major tool is going to be scatter plots, which we'll look at in section 2.4. Then 4.1, we'll do correlation, and the big topic will be 4.2. First, let's save these, just so that they're saved. Be rude to upload blank notes. And now here we are in section 2.4. I thought before we start section 2.4, it might be good to kind of test the waters of the class here today. How do folks feel about plotting with the XY coordinate system? Do you feel like a review would be helpful, or do you feel like you're pretty okay with that? A1 for review? We got a couple. You know, that's good enough for me. Let's do a quick review on the XY coordinate system. That sound all right to everyone? Okay, thanks for responding on that question there. So I'm going to put the official start right here on the notes. And this will just be kind of a warm-up. You know, it wouldn't hurt to just say that. Let's call this warm-up question. Not so much a question, but more practice. If we're dealing with 2 numerical variables, now 1 horizontal axis is not good enough. Sure, you could do things to that. You could put a dot plot on it, a box plot, or even a histogram. But if there is an x variable and a second numeric variable y, then the new plot we want would be really just plotting here. We're going to call this a scatter plot. And so let's say for our problem, plot 3, 2, -4, 0. And let's go with -1, -3. So 3 different points in the XY plane. What we're officially going to be producing is going to be a scatter plot, but that will only take on the name scatter plot once it has the right context of actually dealing with a statistical problem. As it stands, it's really just a math problem. But here's the way we're going to think about it. X here is extremely important. And I want to make that blue since I think that's how the rest of the notes are. It's going to have a name called the explanatory variable. In math, you would have called it the independent variable. And the next variable of massive importance will be y. Y is going to be called the dependent variable. Essentially what we have here is amongst these three different points, an x coordinate and a y coordinate for the x variable and the y variable. So we'll plot the 3, -4, -1, along with its full coordinates. So 3, 2, -4, 0, -1, -3. I'll just plot them in black. First thing we do is we go 3 units for this point on the x-axis. Because it's positive, we'll be going to the right, according to where they intersect the origin here. Then for the 2, we just go up 2. And that's going to be our first point. Does that look right, folks, on that first point here? Awesome. Then down the line, the next one is at -4, 0. So let's go left 4. 1, 2, 3, 4. Because the y coordinate is at 0, we just plot a point right here on the x-axis itself. Then next one, -1, -3 means go left 1 and then down 3. That's where our last point right here would end up. If you wanted to, you could be more specific on these points and say what their actual coordinates are. So if you call these 3, 2, -4, 0, and then -1, -3, then that's pretty helpful, I'd say. Really more for the sake of notes, so that you know which points really went to where once you plotted them. So that's essentially what we're going to be doing. We're going to take 2 variables. There could be lots and lots of data, and there could be a whole cloud of points inside here. Our goal in section 4.2 is to model those points, much like we've been doing with the empirical rule using the normal curve. So say, for example, if we had this kind of setup, suppose we did some really hard study. We have 2 numerical variables, so lots of points like these, and we created the scatter plot. So here we're going to put down just a quick example of our goal. In the scatter plot, the data might look something like this, for example. So there's all of our observations. Looks like, I'm not too sure, something like 20 different observations. I wasn't counting. And with all those data in the scatter plot, here is the major punchline to what we're trying to achieve in chapter 4. This is still section 2.4. We're warming up to it. We want to go here and put a line that gets as close as possible to every single point in the scatter plot. Visually, it could look like this. Because it's a line, it could have equation y equals a plus bx. That's kind of unnatural to me. In a math class, you'd usually call this y equals mx plus b, but in statistics, it'll be usually written in this way. Even our calculator outputs results in that format. So we'll try to get used to this. And we'll call this the least squares. Regression line. So that's our goal in chapter 4. Produce this line, see how to work with it. The good news is the calculator is, once again, a big help for this kind of thing. So it's going to do a lot of the heavy lifting, a lot of the number crunching through the big formulas that we're going to see in the notes. But the hard work is analyzing and understanding what did the calculator produce. If you have this line, how can you compute with it, give practical interpretations using context? That'll be the harder thing about the notes. So it'll take extra time as we go through those. Well, any questions at all, folks, so far with these quick review problem here or the goal down below? Okay, well, that takes us to our official starts of the notes right here. We're not going to have time to get too far into this, but let's go for part A on this one. Well, first, I guess we have to read the actual problem. You know, that is a lot of reading. Let's see where we are on time. We might be in good shape on this, but I think we would probably be rushing. How about we come back to this one at the start of next class? Does that sound all right to folks? It is potentially raining out there, so this might be a good day to end a little bit early. Timing is kind of tricky on these classes because, I mean, just to read this one, get through part A, that's a good 7 minutes on this one. Well, any questions, folks, before we call it a night? Okay, if I did get you your exam back, I have it down below here. Please don't forget to get it. If I missed you on your exam, maybe you're not here today, you're seeing the video on YouTube, I always bring them with me, so just come see me and I'll have them. Well, have a great night, folks, and I'll see you all